Hello everyone, and welcome back to this series on multivariable calculus, and today we're going to be continuing our exploration of optimization of functions and describe one method for constrained optimization known as Lagrange multipliers. So let's just briefly go over some important things that we've already built so far that we're going to need today. So let's assume that we have some contour. Let's work in, for example, R2 domain space. Let's assume that this is one other contour and this is another. Let's assign a couple of elevations. Let's assume 20 is that interior elevation, 35 is that secondary elevation, and then 50 is that last outer elevation. So pretty much what we're looking at here is a valley of sorts in 3 dimensions. Let's pick a point. Let's assume this is our point P here. And what we're going to do is we're going to consider a tangent vector at this particular point, and let's assume that this is our tangent vector t, which is going to be equal to dx dy. So let's also consider that this is our contour C, which is the set of all points xy such that f of xy is equal to some constant. Obviously, P, by definition, is an element of C, and let's assume that P is defined to be equal to x0, y0. So what is so special? So if I were to take the gradient of function f at point P, what would I get? So you should already know that the gradient of f at point P is going to be this vector here. Right, so this is going to be the gradient of f at point P, or equivalently notated as the gradient of f at x0, y0. And keep in mind that the gradient of f and the tangent vector along the contour of P are always going to be orthogonal to one another. Right, so that is the gradient of f at P, dot product with the tangent vector at P is always going to be equal to 0. And we know that it's going to be pointing outwards because it always points in the direction of the greatest rate of change. And if it were to point the other way, that would point down the valley instead of outside of it. All right, so those are some of the things that we have up to this point. So let's suppose we want to optimize. Let's assume we want to optimize G, which is also going to map R2 to R. And when we say optimize, that means we're either going to be looking for the maxima or the minima. Either one is perfectly fine along the contour R. So if we were to look at that path as if it were a straight line, i.e. differentiably deform it into a line, and then look at the elevation of G along that, then it's possible that what we're going to have is something along this form. And let's pretend that this point here is actually the same point P that we built the tangent to for the surface for f. So if we were to pick a vector or take the gradient of it at this point, then the gradient obviously is going to point in that direction. And if we were to take the gradient of G at that point, then it's obviously going to point in that direction. And if we were to take the gradient at point P, then we're going to have one of two cases, right? So this picture is if P is the optimal value of G along R. And you could also equivalently say that P could be the optimal value of f along R, where R is dictated by G of xy is equal to some constant c. So the lucky case, or case 1, is that the gradient of G at point P is equal to 0. That is, it doesn't really matter that we're traversing along the contour R. So what does this mean? That means P is an extrema, max, min, saddle, or neither, of G, and that's obviously regardless of C and or the function f for which C was built from. Or if the gradients of G at P is not equal to 0, keep in mind that the contour C is still defined, so the gradient at point P should still be perpendicular to the tangent at that point, because that's pretty much the properties of gradients regardless of the function. So it still is perpendicular or orthogonal to T, meaning that gradient G dot product with the same tangent vector T will be equal to 0. So combining what we had before, the gradient of f at P times T was equal to 0, and here we have gradient of G at P dot product T is also equal to 0, then we have what? So since gradient f at P dot T equals gradient G at P dot T equals 0, then that means these vectors are parallel to each other. That means their gradients are scalar multiples of each other. So you can say that the gradient of f is equal to a scalar multiple lambda of the gradient of G. And here lambda is assumed to be non-zero, right? Because if it were to be 0, then gradient f, gradient G could be literally anything. So we have this very beautiful result, right? And this means parallel gradients. Okay? So what can we conclude from this analysis? That means if G is optimal along C, then there exists, so backward E means there exists in case you don't know, a lambda not equal to 0, such that the gradient of f is equal to lambda gradient G, or you could also say that gradient G is equal to lambda gradient f if you're looking at it from the other direction. And this lambda not equal to 0, this number is referred to as a Lagrange multiplier. A Lagrange multiplier. That is, by how much is gradient f a scalar multiple of gradient G. So what exactly does this mean? So if we look at this equation in a little bit more detail, then we're going to have what? Keep in mind, gradient of a function is a vector function. So we're going to have fx, fy, so the partial derivatives of f with respect to x and y respectively, will be equal to lambda gx, gy. So if I give you a function f and I give you a constraint g equals c, for example, you can find fx, fy, gx, gy, provided that they're differentiable. And then what we're going to do is we're going to first find lambda, the Lagrange multiplier, and then we're going to find the x, y's, or xy, where xy is going to be the optimal or the location for which the function f is optimal along that path. Now that we have the theory built, let's work through a couple examples to illustrate it. Let's suppose that we want to optimize this linear plane, f of xy equals 4x plus 6y, along the circle x squared plus y squared is equal to 12. And keep in mind, we're optimizing it along the boundary of the circle, not the exterior or its interior. So how are we going to go about solving this? Well, obviously, we're going to use Lagrange multipliers. So what is the gradient of our function f? So the partial derivative of f with respect to x, that's going to be equal to 4. And the gradient of f with respect to g is going to be equal to 6. So if we take this function here, this is going to be our g of x, and that's going to be equal to our constant c, which is going to generate our contour. Then the gradient of g is going to be equal to 2x and 2y. So this is going to give us a few constants once we represent the equation as gradient of f is equal to lambda gradient of g. The first equation is we're going to have the x components of 4 is equal to lambda 2x. So 4 is equal to lambda 2x. And then we're going to have 6 is equal to lambda 2y. And lastly, we have x squared plus y squared is equal to 12. Because keep in mind, we have 3 variables here. We have lambda, x, and y. So ideally, we need at least 3 equations, sometimes less, sometimes more, in order to solve this equation. So the first thing I want to do, and there's several different variations of how to solve systems of nonlinear equations, but what I want to do is I want to solve each of these equations for lambda. So if I solve the first one for lambda, I'm going to have lambda is equal to 4 divided by 2x, or 2 divided by x. And then the last one, I'm going to have lambda is equal to 3 divided by y. And you could also represent that as x is equal to 2 over lambda, and y is equal to 3 over lambda. Depending on your strategies, it depends what you want to do. So if I solve this equation for x and y and substitute both into this last equation, then I should have an equation with only lambda in it. Then I can find lambda, and then I can find the x and y that are associated to it. So once I do that, what will I have? So I'm going to have x squared plus y squared is equal to 12. And then I'm going to have what? So I'm going to have 4 plus 9 is equal to 12 lambda squared. Once I have this, then I can solve this equation for lambda squared. So 9 plus 4, that's going to be equal to 13. So lambda squared is going to be equal to 13 over 12, giving us two values of lambda. Lambda is equal to plus or minus the square root of 13 divided by 12. And you can simplify the square root of 12 if you really want to. So once I have my lambda, then I can find my associated x and y value that is associated to each of them, and then I'm going to have 2 x's and 2 y's for that. So therefore, x is going to be equal to plus or minus 2 square roots of 12 over 13, and y is equal to plus or minus 3 square roots of 12 over 13. And keep in mind, lambda was root 13 over 12, so we're dividing by that. That's why we're flipping those fractions. So we're going to have 2 points associated to this. We're going to have P1, which is going to be equal to 2 square root of 12 over 13, followed by 3 square root of 12 over 13. So that's the plus version. And then we have P2, which is going to be equal to minus 2 root 12 over 13, and minus 3 root 12 over 13. So those are 2 points that are going to be optimal values of a function along this path. So we just need to figure out which one is which, so we're just going to plug them in and see which one is greater. So if we plug in P1 into f, we're going to have 4 times x plus 6 times y. And that's going to give us what? So notice root 12 over 13 is a common factor for both. So it's going to be equal to 8 plus 18 times root 12 over 13. And 18 plus 8 is equal to 26 root 12 over 13. And then you can simplify this if you really want to be 4 times root 39 as your nicer answer. Notice that if we plug in FP2, the only difference is you're going to have a minus sign here, a minus sign here. And since it's just 2 terms added to each other, this is just going to be equal to the negative of FP1. So this is going to be equal to minus 4 root 39. So that's going to be our other value at P2. So notice that this one is the greater, this one is the lesser. Therefore, this is the maximal value of the function, and this is the minimal value of the function along that path generated by the circle. So that means f has a, let's say, maxima of root or 4 root 39 at P1, and it has a minima of minus 4 root 39 at point P2 in its domain along R, which is the set of all points x, y, such that x squared plus y squared is equal to 12. So that's how you can find optimal values of functions along a boundary. Keep in mind that a smooth function f is either optimal when the gradient of f is equal to 0 and the determinant of the Hessian of the function is greater than 0. Because if the determinant of the Hessian is less than 0, then it is a saddle point. And if it's equal to 0, that's inconclusive. Or when the function attains boundary values with respect to its domain. And keep in mind, in case you don't remember when gradient is equal to 0, how to classify it as a max or min. So the determinant of the Hessian matrix, which is the matrix of all second-order partials, has a determinant that's positive. Then if fxx at the point is positive, that's pretty much our concave up from calculus 1. That's going to be a min, and when fxx is less than 0, then that's kind of our concave down from calc 1, so that's going to be our local max. So with this in mind, let's consider the following example. Let's assume we want to optimize fxy equals e to the minus xy on the region x squared plus 4y squared, so now it's an ellipse, less than or equal to 1. So this is the interior of an ellipse, right? So pretty much what we're looking at is an ellipse like this, and we want to find the optimal value either on the boundary or its interior, okay? I want to optimize this function along that region. So let's first off find the Lagrange multipliers if we can. So what we want to do is we want to solve gradient of f is equal to lambda gradient of g. So when we do that, what do we get? So what is the gradient of f? So the gradient of f is equal to, so take the derivative with respect to x, y is going to come down, and keep in mind there's a negative sign as well. So we're going to have minus y, e to the minus xy, is equal to lambda times the derivative of g with respect to x, that's going to be equal to 2x, and then we're going to have minus x e to the minus xy is equal to lambda times the partial derivative of g with respect to y, and that's going to be equal to 8y. Here, what I want to do, because that e to the minus xy is going to cause some problems, I'm going to divide these equations into each other. And one could ask, well, what if x and y are equal to 0? We'll take care of that point in just a moment. So let's assume that xy is not equal to 0, 0. So if I can do that, if I can assume that, then I can divide these two equations. So I'm going to have positive y over x is equal to, so the lambdas are going to cancel on the right-hand side, leaving us with 2 divided by 8, which is going to be 1 over 4, and then we're going to have x over y. Cross multiply, and that's going to give you 4y squared is equal to x squared. Therefore, x is equal to plus or minus 2y. Right? So the Lagrange multipliers are in some sense located along this line. So let's see if we can find such points. So what I want to do is I want to take this equation and substitute that into our constraint on the boundary, because that's where Lagrange multipliers are going to be finding the optimal values. So that's going to be equal to plus or minus 2y squared plus 4y squared will be equal to 1. And plus or minus 2 squared, that's going to be equal to 4. So we're going to have 4y squared plus 4y squared, which is going to be equal to 8y squared. That's going to be equal to 1. So that means y squared must be equal to 1 over 8, which means that y is equal to the square root of that, plus or minus the square root of that. So plus or minus 1 over the square root of 8. Or you could write that as plus or minus root 2 over 4 if it makes you more comfortable. So that's where the optimal values are located. And then we're going to have x, which is going to be equal to plus or minus 2. So plus or minus 2, so we're going to be using this equation, plus or minus 2 times the values of y, which is plus or minus root 2 divided by 2, which is again plus or minus root 2 over 2. So these are x values, and notice that these plus or minus values are independent of each other, so we're going to have 4 points of interest. So our points are going to be point 1, so it's going to be the both positive version, so both positive, and then we're going to have the both negative version, both negative, and then we're going to have the 1 positive, 1 negative, so let's do root 2 over 2, root 2 over 4 negative, and point 4 will be minus root 2 over 2, positive root 2 over 4. Let's plug each of these points in to see which one's the bigger and the lesser. So if we evaluate f at point 1, that's going to be equal to e to the minus root 2 over 2, root 2 over 4, which is going to be equal to e to the minus 2 over 8, which is going to be equal to e to the minus 1 over 4. Notice that that's going to be the same if both of them are negative, so that's also going to be equal to f of p2. And if we do p3, so f of p3, that's going to be equal to e to the minus root 2 over 2 minus root 2 over 4. That's going to be the same but positive, so that's going to be equal to e to the 1 over 4, and that's going to be also the same for the value of fp4. And notice that fp4, this is going to be obviously less than 1. E to the minus something, that's going to be less than 1. And this value is going to be slightly bigger than 1. That's going to be approximately 1.28. Okay. So that's the optimal values along the boundary. So these are obviously going to be equal to minimum values, and these are obviously going to be equal to maximal values along the boundary. Now let us figure out what's going on the interior of the domain. So the gradient of f, again, is equal to minus y e to the minus xy, and then minus x e to the minus xy. And we want to solve this when it's equal to 0, the 0 vector. And that only occurs when xy is equal to 0, 0, which is on the interior of our boundary, which is the point that we sort of accepted or deleted from our logic for our boundary points, which is perfectly fine now. So this is where the gradient is equal to 0, so it's either a max, a min, or a saddle. So if you plug in at the point 0, 0, you're going to get e to the 0, or e to the minus 0 times 0, which is equal to 1. And you then would have to find the Hessian of this matrix, or Hessian of this function, and then find the determinant, and then see whether it's positive, negative, or 0 at this point. But I want to leave it as an exercise for you because I think it's not too bad. But I leave it to you to verify that this is a maximum. Right? Intuitively, you can see that e to the minus xy should go down as x and y go positive. And then you can sort of dance around, because this is sort of like e to the minus x times x, which is e to the minus x squared. And if you don't know what that looks like, it almost looks like a Gaussian, right? But I leave it to you to formally verify that this is indeed a maximum. So what we have here is we have two minima, two maxima along the boundary, and we have a maxima on the interior of our contour. So let's just summarize everything here. So we have a minima, so the function is minima, at root 2 over 2, root 2 over 4, e to the minus 1 over 4, and minus root 2 over 2, minus root 2 over 4, e to the minus 1, 4. And we have a maxima at minus root 2 over 2, positive root 2 over 4, e to the positive 1/4. We also have one at root 2 over 2, negative root 2 over 4, e to the 1/4, and we also have one at 0, 0, 1. Keep in mind, e to the power of 1/4 is slightly bigger than 1, so this is obviously the lesser of the maxima, and these are the greater maxima of the function, right? So therefore, this function has local optima at these 5 points. So that's how you can use Lagrange multipliers to find how to optimize a function along the boundary of a region, and also we can go back to gradients to sort of find the optimal values of the function on the interiors, provided that the function is smooth so you can differentiate it. Hope you enjoyed this video, and I'll see you in the next one. Take care.